Welcome back to your bedtime lessons again. Tonight's bedtime lesson is about lunar eclipses and a bit of solar eclipses too. We're going to do two parts of lunar eclipses and one part of solar eclipses. Here we go. The first one out of the two. Why does the moon turn red? The moon doesn't have any light. The moon does not have any light of its own. It shines because its surface reflects the sunlight. During a total eclipse, the Earth moves between the sun and the moon and cuts off the moon's light supply. When this happens, the surface of the moon takes on a reddish glow instead of going completely dark. The red colour of a totally eclipsed moon has been prompted many people in recent years to refer to total lunar eclipses as blood moons. But why does it turn red, though? The reason why the moon takes on a reddish colour during totality is a phenomenon called Rayleigh scattering. It is the same mechanism responsible for causing colourful sunrises and sunsets, and for the sky to look blue. Colourful sunlight. Even though sunlight may look white to human eyes, it is actually composed of different colours. These colours are visible through a prism or in a rainbow. Colours towards the red part of the spectrum have longer wavelengths and lower frequencies compared to colours upwards towards the violet part of the spectrum, which have shorter wavelengths and higher frequencies. Earth's atmosphere. The next piece of the puzzle, why a total eclipse turns red, the moon turns red, is the Earth's atmosphere. The layer of air surrounding our planet is made up of different gases, water droplets and dust particles. When sunlight entering the Earth's atmosphere strikes the particles that are smaller than the light's wavelengths, it gets scattered into different directions. Not all colours in the light spectrum, however, are equally scattered. Colours with shorter wavelengths, especially the violet and blue, are scattered more strongly, so they are removed from the sunlight before it hits the surface of the moon during a lunar eclipse. Those with longer wavelengths like red and orange pass through the atmosphere. This red-orange light is then bent or refracted around Earth, hitting the surface of the moon and giving it the reddish-orange glow that the total lunar eclipses are famous for. Look for the blue band. Veteran eclipse watchers will tell you that if you look really hard right at the beginning and just before the end of totality, you might detect a light blue or turquoise band of the moon's face. This happens because the Earth's ozone layer scatters red light and lets through some of the blue light that is otherwise filtered out by other layers of the atmosphere. Many shades of red. The moon can take on different shades of red, orange or gold during a total eclipse, depending on the conditions of the Earth's atmosphere at the time of the eclipse. The amount of dust particles, water droplets, clouds and mist can all have an effect of the shade of red. Volcanic ash and dust in the atmosphere can also lead to the moon turning dark during an eclipse. Fun fact, if you were lucky enough to see a total eclipse from the moon, you'd see a red ring around the Earth. In effect, you'd be seeing all the sunrises and sunsets taking place at that specific moment on Earth. The first one is very dark, the moon almost invisible. 1 is dark eclipse. 2 is the rust-coloured eclipse, the brick red eclipse, and copper red or orange. Brightness scale. There we are. Scientists measure the appearance and brightness of a total eclipse using a 5-point scale ranging from 0 to 4, called the Danjon scale. A lunar eclipse is ranked and assigned on a value of the scale at a time of mid-totality. Let's go to the second part. The second part of this eclipse is what are they and why are they special? Eclipses need a new or full moon. The basic requirement for a solar eclipse is a new moon, which occurs when the moon passes between the Earth and the Sun. A lunar eclipse, however, requires a full moon, when the moon is on the opposite side of the Earth to the Sun. The moon takes around 29.5 days to go through all of its phases, and new moons and full moons are separated by about 2 weeks. Eclipses don't happen every month. The moon's orbit around Earth is tilted by about 5.1 degrees to Earth's orbit around the sun. This is why eclipses don't happen every month. At new moon and at full moon, more often than not, the moon is too high or too low to align precisely with the Earth and sun. Eclipses come in seasons. About every 6 months, Earth comes to a sweet spot in its orbit where a perfect or almost perfect three-way alignment on the Earth, Moon and Sun can occur. Each sweet spot lasts for about 34.5 days an eclipse season. If there's a new moon near the middle of an eclipse season, it will form a straight line with the Earth and the Sun. This result will be a total solar eclipse, or an annular solar eclipse, if the moon is too far from Earth to completely cover the Sun completely. In a similar way, a full moon near the middle of an eclipse will produce a total lunar eclipse. On the other hand, if a new moon or full moon comes near the beginning or end of an eclipse season, the three-way alignment will not be quite perfect. In this case, the result will be either a partial solar eclipse, a partial lunar eclipse, or if the moon passes through only the faint outer part of the Earth's shadow, a penumbral lunar eclipse occurs. Time for our final part. Our final part is about what can you see during an annular eclipse. 90 minutes before annularity, partial eclipse begins. The moment the edge of the moon appears to touch the edge of the sun is called first contact. Eclipse glasses must always be used for looking at the sun. At no point during an annular eclipse does the moon completely cover the sun. 60 minutes before totality, obscuration of 25%. The eclipse progresses. 1/4 of the area of the sun's disk is now covered by the moon. 50 minutes before annularity, temperature changes. As the moon continues to cover up the sun, the amount of solar energy reaching the ground decreases, causing a drop in air temperature. 45 minutes before annularity, sharp and blurry shadows. Shadow edges that are aligned with the sun's narrowing crescent start to become sharper. Edges that lie at right angles at the sun crescent shape remain more blurry. 30 minutes before annularity, sky darkens. With around 2/3 of the sun's disk now covered by the moon, the sky starts to become noticeably darker. 20 minutes before annularity, temperature, humidity and wind. Conditions on the ground and in the atmosphere continue to change as the amount of solar energy decreases. The moon's shadow can cause small changes in wind strength and direction. 15 minutes before annularity, light level and colours. The surroundings start to darken, while colours begin to turn a bit greyish. The moon now eclipses more than 3/4 of the sun disk. 10 minutes before annularity, nature reacts.